Alright, empirical formulas. It's just what it says. It is the lowest whole number ratio. It just means that it can't be broken down. So if you had something like N6O3, we would break that down or reduce it just like a fraction to N2O. Now if you really want to, you can put the 1 right there, but it's certainly not necessary. So it's the lowest whole number ratio. And the whole number ratio is important because you can never have something like N 1.5. Here's a couple of examples. The molecular formula, which we're going to talk about a little bit later, not today, you can see that it can clearly be broken down. You have a 2 and a 4. And for an empirical formula, we simply reduce that and break it down. It cannot be further broken down. And again, kind of think of fractions, if you will. 2 over 4 would break down into 1 over 2. So it's the lowest whole number ratio. Here's a problem, and this is kind of how empirical formula problems are written. They're written by percentages, and we always treat the percentages as grams. So you can see 25.9% nitrogen, we treat as 25.9 grams of nitrogen. We want to convert that into moles because that ratio or relationship in an empirical formula is a mole relationship. We divide it by 14 because that's the mass of nitrogen, and that gives you 1.85 moles. We have to do the same thing for oxygen. Here's 74.1% we treat as 74.1 grams of oxygen. Again, we divide it by 16 because that's the mass of oxygen on the periodic table. Now some of you are thinking, wait a second, it's diatomic. But again, oxygen is only diatomic when it's by itself, and in this situation it's actually in a problem. So here we go. We have our two mole relationships, and that's the ratio we're going to use to determine what the actual formula is. The next step is we divide them both by the smallest number of moles. So we have 1.85 and 4.63. Obviously 1.85 is much smaller than 4.63, so we divide them both by 1.85. Divided by itself, obviously it's going to give you 1. 4.63 divided by 1.85 is going to give you 2.5. Now what we have is we have a ratio, or certainly not a final formula, but our formula right now is N1 or NO2.5. Now we went back, we remember that you have to have whole numbers and you can't have a 0.5 or any kind of decimal like that. What we end up doing here is we multiply everything by 2. And we simply do that to get rid of this 2.5. We can't have that. Why did I multiply by 2? Well, that's the smallest number I can multiply by to get a formula that works with no partial numbers, with only whole numbers. Our final formula is N2O5. That is an empirical formula because 2 and 5 aren't divisible. We cannot break that down any further. Here's another example and something really similar. Again, even though they're giving us percentages, we treat those as grams. So 5.9% hydrogen and 94.1% oxygen, we treat those and turn those into, or just say that they're. So 5.9 grams of hydrogen. Hydrogen is an easy one because we're always dividing it by 1 because that's the mass of hydrogen. So whatever you start with hydrogen is always what you'll get. 5.9 grams equals 5.9 moles. Hi, honey. Thank you. Can you wait a minute? Okay. There you go. Sorry, minor commercial interruption there. We need to do the same thing with oxygen. 9.1% is 94.1 grams. And we divide that by 16. That's the mass. You can see our two final answers are 5.9 moles and 5.88. Obviously very similar. When we divide those by the smaller number, which is 5.88, we're going to get a 1-to-1 ratio. Okay, 1 mole of hydrogen for every 1 mole of oxygen. And our ratio is 1-to-1. You can write it as HO. You can write it as H1O1. Obviously, we don't write that very often. We usually ignore the ones or they're just understood. But the final empirical formula is HO. We know that this is correct, smiley face, because it's reduced. We cannot further reduce down HO or H1O1. One more example here. What's the empirical formula of a compound that's 79.8% carbon and 20.2% hydrogen? We're going to do the same thing. Take your percentages. We're going to make them into grams. And we'll divide 79.8 grams by 12. That's, whoa, that was crazy. Because that's the mass of carbon, 6.65 moles of carbon. Again, anytime you're dealing with hydrogen, you're just going to get what you started with because you're always dividing by 1. The next step is to divide those both. It's a ratio, so we divide by the smaller number of moles. 6.65 is smaller than 20.2. So we divided both by 6.65. It comes up with 1 mole of carbon and 3 moles of hydrogen. Again, here's our ratio, C1H3, or most of the time we'll just write it as CH3. And again, that is an empirical formula because it can't be broken down any further. Now, here's some problems to go ahead and do on your own. If you move forward on your notes, you'll see that the answers are there, but these are some that you should just try to do, and certainly if you get stuck or feel like you need to work with a partner, that's wonderful.